So in the last few years, a number more have been discovered. In fact, several have come out just in the months while I've been writing this course. And so this is a fast-moving field. And these things are massive and far out and typical borderline brown dwarf planets, depending on your exact age and modelling.
But we only have a handful, Paul. And you know, you don't learn much from a handful. You got to go poll to find out who the next prime minister is. You don't ask 5 people. You need to ask a lot of people. So it strikes me we need a survey, a big survey, to go out and really see what's going on.
And you want to look systematically at a whole range of stars and see how common are these things, what sort of stars they found around.
Right.
And the technology is getting much better. We have a whole bunch of new instruments coming along, which both using this angular differential imaging and some new tricks. For example, what you can do is you can observe simultaneously at 2 different wavelengths. One wavelength where you expect these planets to be bright and one where you expect it to be faint.
So you'd look at them where the methane isn't causing you problems and where it is, presumably.
Yeah, and all the interference from the star should be the same at both wavelengths, whereas the signal from a planet should only be at 1. So you can use that to discriminate between the two, subtract off the star contamination and just see what's left over.
So this kind of shows that we're doing pretty well because, remember, this is our magnitude difference. So this is talking about the ratio of how faint we can see relative to the star. And that's 15 magnitudes. So that's 5 plus 5 plus 5. So that's 100, 100, 100, a million. So we're getting down into very, very close to you know, where we want to be. We're down below a million now. So that's getting where we need to be able to see these planets.
Yeah, so maybe a million, maybe even 10 million. It's still not a billion. We've still got another 100 to go. But
Yep.
so that's a vast improvement. So there is a problem with this, which is typically whenever you take a picture of a star with this, you'll indeed see lots of little dots near it. Think, yay, we've got planets. But then you actually discover that they're not planets, they're just background stars.
Because there's a lot of stars out in the sky, unfortunately.
So what you have to do is go back and take a picture a year later and see if all these dots have moved with your bright nearby star. And if they haven't, they were background things that were left behind. But if you do all that, you find nothing.
Nothing. So the first ones we see things, and then we go and look at 57 objects and find nothing?
Yep, so these are recent results. There have been a number of big surveys done, and they seem to be finding very little. Maybe one object, maybe nothing. This is a particular survey done at Gemini, and they looked at 57 of these debris disk stars, these big, bright stars, exactly the places where we've seen all these things so far. And nothing. If these things really did start hot, and were therefore very, very bright when they're young, this allows us to put an upper limit. You can't have something more than 40 astronomical units out, so beyond the orbit of Pluto, that weighs more than 3 Jupiter masses in more than 21% of them from this survey. And other surveys are coming with similar sort of things.
So they're not everywhere, although that isn't completely constraining. But it's saying that we may have gotten lucky in these first few things at Beta Pic and Fomalhaut, etc.
HGH 799 seems to be unusual. It's in that 20%, not the rest. People have done more surveys. For example, they look around other hot stars, ones which don't have debris disks. In these cases, they get fewer than 10% have these analogues. They could also look about maybe not these very massive stars, but more normal stars. So there aren't that many stars that are both nearby and so young that the planets are still glowing like crazy.
Yep.
But when those that are, fewer than 10% have something that weighs between 1 and 20 Jupiter masses, between 10 and 150 astronomical units out.
All right, so we're, I guess, getting a good look at the nearby universe, but then this has to be reconciled, I guess, with all these free-floating planets and the planet rates that we're seeing from microlensing. So microlensing not just tells us about free-floating planets, it also tells us about planets a fair ways out around normal stars.
Yeah, remember from microlensing we saw the little tiny glitches just from a planet, and all we knew from that glitch is that it had to be more than about 10 astronomical units from the planet. So it could have been a planet a long way out or a free-floating one. But there was an average, something like 1.8 of these tiny things per star, whereas what we're telling us here is that fewer than 10% of stars have planets out there. This is the other half of the argument for why they must be free-floating, because if they really were in orbit around the planets, this would be more like 200%, not 10%. So it looks like there really are free-floating planets, and these massive things a long way out do exist, but they're not common.